in the same band here, they will map, virtually by definition, into the same element of this group. All right. Second example involving matrices, 2 by 2 square invertible matrices. So that's your set. That's your G. Right. And then binary operation on matrices, just matrix multiplication. So that's what the binary operator for G is. And the entries in the 2 by 2 will have 4 entries in the matrix, and they are real numbers, right? Real numbers, not complex numbers. So we're talking about real matrices. Okay. Now, invertible. What does that mean? It means that a matrix B exists, which in effect is the inverse of this matrix A. So, BA equals AB equals I, the unit matrix, right? And criterion for A to have an inverse B, so you can write the inverse of A like this, right? It's sort of a shorthand. And criterion for that A inverse can be found from A is that its determinant, the determinant of this square matrix, is not equal to 0. Now look, that's taking results from linear algebra, and I will definitely be giving a course as one of my core courses. At undergrad level, I'll be giving about a dozen or so core courses before I move on to M1, first year master's level. And these undergrad level courses, and this finite group theory is the very first in the undergrad level courses of about a dozen or so. And another one is linear algebra. So, and here's the textbook that I'll be using for that course when I come to do it in several months, I guess. The author, well, there's only one author this time, is Lang, Serge Lang, Lang, famous name in mathematics. Title of the book is Introduction to Linear Algebra, it's second edition. Now, the reason for giving a whole course on linear algebra is linear algebra just crops up all the time. So it's I consider it essential that if you're following these courses right up to PhD 2 level, and you're living in, say, a third world country, and you can't afford to go to university, then you may not have sufficient background if I just start at graduate level. So in certain topics that are absolutely basic and essential to what I'm trying to do with the math and physics at higher level, if you don't have that basis, even undergrad basis, then you'll have a hard time. So the simple solution to that is just simply teach these fundamentally important basic courses, and linear algebra is one of them. Right? Okay. Now, so this is a second example of a homomorphic function. So this function f is mapping matrices, 2 by 2 invertible matrices, into the non-zero real numbers. And this is your group H, and its binary operation is just multiply, just simple multiplication of real numbers. Okay, so that's mapping this group to this group. So what are you mapping in terms of element? So here you're mapping an element to some other element. Now A is just a 2 by 2 invertible matrix, which is a member of this group, this set, if you like. And this det here, det, that means determinant, the determinant of matrix A. And since the criterion for A, matrix A, to be invertible is that determinant A is non-zero, okay, So this determinant here is non-zero, so it's well formed, well defined. Right? Now, how do we prove that this mapping F is homomorphic? Well, we have to show this, right? That's the criterion for homomorphism, that your function F is a homomorphic function, that the mapping is homomorphic. Different ways of saying the same thing. Right? Well, again, we're starting on the right-hand side, trying to prove the left-hand side. So we're mapping matrices into real numbers, non-zero real numbers, right? So F of a matrix A times F of another matrix B. Now, given this, right, F of A is determinant of A, so FA/FB will be determinant A times determinant B. Now, a determinant is just the number, right? Just a real number. Okay. So determinant A, determinant B is just the product of two real numbers. Okay. Now, out of linear algebra, out of the theory of matrices and determinants and vector spaces and eigenfunctions and eigenvalues and diagonalization of matrices and all those techniques, which I will teach in detail in a whole course on linear algebra. One of the things we know, if you don't know this, you're just going to have to take it for granted, just accept it until we actually do the course on linear algebra. But the determinant of A times the determinant of B, so in other words, the product of two determinants is equal to the determinant of the product of the two matrices. So det A, det B equals det of AB. Right? That's a standard result that comes out of linear algebra. Probably a lot of you are quite familiar with this, but in case not, just be patient. A couple of months, I will be teaching a whole course on linear algebra. Right? The book is by Lang, or Lang, L-A-N-G. All right. Now look, det of a matrix, the determinant of a matrix is your F, right? So det of something is just F of something. Well, what's the something? Well, it's AB, right? Det of AB is F of AB. Therefore, this equals that, right? And that's the criterion for homomorphism. Okay. Now, interestingly, and this is a sort of a foretaste of what's coming in a later session of this lecture, that if the number, the real number that gets mapped to, right? So if some matrix A, if you map F of that matrix, and what it gets mapped to is 1, so if your real number is just 1, then that means the determinant of this matrix is 1. And there's a whole theory coming later about such matrices. Lie theory and classification of elementary particles uses this property that the determinant of a matrix is 1. Right? And giving you a taste of what's to come at higher levels, at M1, M2 level, in math and physics. Right? Okay. Now, right, so that's the end of 2 examples. Now we get a bit more back to theory, and then running out of board. Now, can you remember the discussion of, in chapter 11 on isomorphism? We were asking the questions, does the unit of group G, under this mapping, does it map to the unit of your second group, your target group? Now, we proved that was true. If you want to go back and look at that proof in chapter 11, so lecture 11, it was theorem 35, quite a while back. So if you want to refresh your memory on the proof in the context of isomorphism, that if you map the unit in your domain, your starting group, if you like, you will get the unit in your codomain, or your target group, right? You will get this. And so same question for homomorphism. If f is a homomorphic function, will it still map the unit of g into the unit of h? So it's a related question. And a similar question is the inverses in G, in your first group. Do they map into the inverses of what you get, the image, if you like, in the second group, in H? So do inverses map? Do the units, does the unit map? Does the inverse map? Now, the answer is yes, and the proof is in 35. Now, I'm saving a bit of time here. Now, we could just do a complete repeat, but we've done it already. So just go back to lecture 11 and have a look at the proof of theorem 35, because the proof here, to prove this, is just the same proof as in 35. So I'm not going to just spell it all out again, because it's just a complete repeat, right? And why do I say that? Well, because the isomorphic proof, showing that the unit maps and the inverses map, that proof in theorem 35, in chapter 11, in other words, lecture 11, that proof had nothing to do with bijection. Right? Did not use the concept of bijection. It only used this kind of thing. It only involved that, right? And that criterion there is equally valid for isomorphism as it is for homomorphism, right? Therefore, the proof that the units map and the inverses map, that proof in the isomorphic case also holds for the homomorphic case. It's the same proof, right? So therefore, it's a repeat, so I won't do it. I'll just simply state that theorem 61 is, it just says so, that the mapping of the unit of your G is equal to the unit of your H, right? So the unit maps, and if you map G's any element of your group G. If you map that little g into H, so this is a member of your second group, H. So if you map then the inverse of G, so do the inverses of big G, do they map into H inverses? So do the inverses of G map into the inverses of H? So here are the inverses of G, right? Little g, so G inverse. Then f of G inverse is the inverse of H, right? So if that's true, then this homomorphic mapping will map G inverse into H inverse. Now all that theorem 61, the proof, we've already done it. It's in 35. As I said, the reason for that is that this proof here in theorem 35 only involved this, had nothing to do with bijection. Okay, so it's valid for both cases of isomorphic mapping and homomorphic mapping. Okay, well, I've run out of board, so I will stop there. Now I have to switch off the camera. I have to walk around the bed, so it takes a bit longer.